Hi, so this is Charles Ringham, this is Jake Park, and I'm Evan Graham, and we are the missing dog group.
Chose to do the Steganography project, which involves hiding multiple images inside another Doge meme or just one image.
Evan was responsible for the expand, flatten, and even and odd hiding method. Charles was responsible for ending in 7 string method and prime method, and I was responsible for making the GUI.
First, I want to point out that the GUI is identical for all 3 methods, so I'll be going over the first hide and recover pages, and the rest of the methods will work the same way. So here I'll be explaining the callback functions, and then the load dog image button right here. This button basically reads dogimage.png and shows the image at the designated UI axes. And I'll move on to the drop-down menu. Here, the user can choose all 10 images, and the image will be loaded on the designated UI axes. It basically works like the load dog image button. However, it sets app.hiddenImage to the corresponding image the user chose for later use in the hide image button. For example, if the user chooses image 7 from the drop-down menu, it'll set app.hiddenImage to 7. Now I'm going to explain the hide images callback function. The hide image button basically works by reading the selected images from the drop-down menu and putting those in the embed function, and it displays the result and saves the result as embedded, even, and odd. Next, I'll be explaining the load embedded image callback. Again, this just works like the load dog image button, so I'll be skipping the explanation. Lastly, I'll be explaining the recover callback. But here, the recover callback will recover the hidden images, and the job of this button is to display each result onto designated UI axes. This is done by setting the UI axis we want to display the image on as parent. For example, it says mshow expanded image R parent app.UI axis 6-4. So this expanded image R is going to be displayed on app UI axis 6-4.
So when flattening each image, we are basically taking every value or color in an image on a grayscale from 0 to 255 and turning it into either a 0 or a 1. When going line by line, we can see that the function flatten hidden flattens whichever image placed in the image to hide section by looking at each pixel on a 400 by 400 grid in an image. This grid is defined in an X and Y format using I as X and J as Y. To be specific, we use a nested for loop with the I and J parameters and state that if the value of the color in position I, J is less than 150, then we turn the number into a 0, which the computer reads as black. If the value is above 150, then it will be replaced with a 1, which the computer then reads as white. So to expand an image from black and white ones and zeros matrix back to a grayscale 0 to 255 value, we created a function called expanded image, which takes the recovered hidden image with the ones and zeros matrix and applies the mat2gray function, which converts the matrix to a grayscale image. Then we create a window for the image with figure and display it with IMShow. And that's basically it for the function expanded image.
This is a demonstration of the even and odd embed technique. So load in the original dog image, select any of the 10 images that we have to hide, and hide them. They go into a new file which has them embedded within them. Then go load it in the Recover tab, and then click Recover, and they come up.
Okay, so for the first embedding technique, we utilize nested for loops, like in the flatten function, to define the area the function will work in, being 400 by 400. Inside of these for loops, we have an if statement, which looks to see if the selected flattened image has a 1 or a 0 at each point in the 400 by 400 matrix. If a point equates to 0, then it will check if the Doge image has an even number in that same slot. And if so, it will make it odd. If the point equates to 1, then it will check if the Doge image has an even number in that same spot. And if so, it will make the number even. What this does is that it makes the embedded Doge image, and it sees if, say, the value of that Doge image at a certain spot is 241 at coordinate 25,78, right? Then we know that the hidden image will be black at that same point because it's an odd number. It's ending in an odd number. And then so it's like vice versa. If it was 240 at that same point, then we would know that it's white because it's an even number. And that's basically the gist of the even and odd technique.
So here's a demonstration of the embed technique where the pixel values end in the number 7. Load in the dog image, the original one. Select any of these images, and then I'm going to change this one here. And then hide it. This one takes a couple seconds. It goes into a new file again. There it is. And then load that embedded image, the same one, and it recovers the same images. Embed technique where the pixel values end in the number 7. First, an empty string matrix 400 by 400 is created. It runs through every pixel in a nested for loop. And first, it checks for any pixels that currently end in the number 7 and gets rid of them. So here, then once all those have been cleared, if the value in the flattened hidden image is a 0, which means black, then it makes this respective color channel that we're hiding the image in, makes that pixel value a 7. So then in the recover technique, basically it creates an empty matrix first of unsigned integer 8, 400 by 400, another nested for loop for each pixel. It checks if the string ends with a 7, then that value in the recovered hidden image is a 0, which will show up as black, and then if not, 1 for white. And here's the final embedding and recovering technique, which involves prime numbers. There, the image has now showed up. And now for the recovery. There they are. So here's the explanation of the third embedding technique, which involves prime numbers. Again, a nested for loop to run through every single pixel. And first, the function checks if a current pixel value is currently a prime number and makes it not 1 by subtracting 1. And this is because so there are no random black spots, just like in the other one, showing up in the final recovered image. And then basically, if the flattened image, the flattened hidden image has a value of 0 or black, the respective pixel in the color array that we're hiding this image in is set to a prime number through the function next prime. And then in the recover technique, it runs the same function isPrime. Basically, if that number is prime, it's set to 0, which is black, and then 1 if not.